this, that we have a like amorphous structure. When I give a right order state, and then sorry order state, then if I give a high current pulse, then melt it and then form again to amorphous state. So you can write, erase, read all the all the operations in a single material, and it's also for how many? It's the transition is in nanoseconds. About 9. I think 9 nanoseconds. The transition. So it's very high speed actually. But also you can hold the information for long years actually, at even 120 degrees like that. 10 years. Even the temperature is more than 100, you can store the information. And also you can do a lot of times, cycling, right? You can write, erase, write, erase, all these things you can do without degradation of material. So that's what one of the important property of this material. So I just thank these people. Like this is my supervisor. So who introduced me to these amorphous materials. And this is the ocean ski, right? The red man. Just school dropout, 600 patents, right? So many people have worked on it. He just passed away in 2012. Right? There is an award in amorphous community that in his name. Right? And this is my postdoctoral supervisor, Arun Vashnaya. I just learned a lot from him actually. So he's. I just want to tell just another 2 minutes. Yes, sir. Right? Arun Vashnaya, right? So US. I just did postdoctoral fellowship with him. He owns a company called Saxon Technologies. Right? So you remember initially I told when I show the volume versus temperature, I can with right different cooling rate I can change the volume, right? So that has many applications. So one of the applications is that strengthening the glasses, right? When you prepare glasses, it's in a high temperature state you are taking it to the low temperature. It's a lot of stress and strain in the material. So you just small and you just do this, it will break actually. So how they strengthen the material, they take it to the glass sunshine temperature, anneal it for long hours, 6 7 hours. Then it slowly release the stress and then it becomes soft, right? If you would have seen the old movies, right, in the climax, right, fighting and things, you can see the glass windows broke, and then the glass windows are very big and sharp, actually, right? But they're all just annealed glasses, not strengthened glasses. Whereas nowadays, what they do, right, you take a glass slab and then take it to the glass temperature where it softens, and then you cool the surfaces with cooling jet, right? The surface gets cooled fast, and the inside is still in the soft state. So surface shrinks actually. Both the surface shrinks and then pulls the inner core, right? So, but inner core is trying to pull the outside. So the outside is in the tensile stress, and inside is in the compressive strength. What happens after some time? The inner core also cools actually, right? Now it becomes rigid. It tries to pull the outside, outer layer from both sides, and it becomes the tensile, and the outside becomes compressive. So the compressive stress is about at least 3 times higher strength than the tensile stress. So all these glasses are strengthened like that. So even if it breaks, your windshield, car windshield, even if it breaks into small pieces, not sharp pieces. It's not much harmful, no, right? So that thing. So, but what he did actually, right? So in the US, in the countryside, the village side, if you travel right in a car or something, there is a high chance that the forest bees, right, can bite you. There are some of the forest bees are poisonous, fatal actually, right? If you don't inject the medicine within 30 seconds or so, and you will lose your conscience and then your movement, and then it's after some time, maybe 30 minutes or so, it is fatal actually, right? So what they have, there is something called epic pen, right? So it's loaded with the medicine they take with them, right? So when if it bites, then what they have to just take the thing and inject in the thigh like this, some angle, right? So what do you do? Like when once the bites, you will be under tension, right? Fear, scary. So you will be shivering, and then doing this. So most of the time, the tilted, it gets break. The glass gets break, right? So that is really fatal, more fatal than the debate, actually, right? What Ashley has contributed, it's a great contribution to humankind. So he, mastered a technique called ion exchange, glass strengthening by ion exchange. For example, these glasses, like your glass slide, what you are using in your lab and other things for thinking the portion of any other optical studies, are all soda lime glasses, right? The SiO2 is, melts at about 1700 degrees centigrade. You need to have a fire, very, very high energy to melt it or work with that. So people added sodium, Na2 to that to cut the SiO2 bonds so that the matrix get loosened. So the strength comes down. So the workable temperature is about 600 degrees centigrade now, right? So, so what I'm trying to say is there's a sodium atom in the glasses, right? Usable, whatever you're using nowadays, right? So what he does, he make a K-OH solution, potassium hydroxide solution. Potassium is the same group, sodium, potassium. Potassium is a bigger atom, sodium is a smaller atom, right? So he put it in the solution, the potassium diffuses into the structure and replaces sodium and sits there. So it's a bigger atom. For example, you are traveling, right? Three-seater, and it's all lean people. Now somebody get down and some fat people come and sit between you. You squeeze, right? So, so this puts compressive stress onto the structure, right? So by replacing smaller sodium atom by potassium, he made it so he made more compressive stress to the structure, and it got centered actually. So now this doesn't break actually nowadays. So he wants the whole US market, about 90-95%. He wants the market. Though he is, getting profit, but it's a huge contribution to the human strengthening the glasses actually, right? So, there is a great privilege to work with him, learn a lot of things, right? So with that, I just thank you for listening. Uh, Thank you very much. Right? If you have any questions, you can ask. I can plan. Okay, thank you then.
I would like to invite Dr. K. Satyapandi to provide a memento. Thank you so much, sir, for your inspiring, thought-provoking, and informative speech. Your insights and expertise have truly enriched our conference. It will be very useful for students present here. It is our pleasure to welcome Dr. K. Satyapandi, Professor of Physics and Research Coordinator at the prestigious SRMTRP Engineering College, Trichy. A renowned academician and researcher, Dr. Shakti Pandey's expertise in physics has inspired generations of students and contributed significantly to the field. He has published more than 150 papers, reputed international journals, and organized many FDPs and conferences in the field of science and technology. I would like to call upon Dr. K. Satyapandi on the stage to continue the session.
Thank you. First and foremost, I'm thankful to God Almighty for organizing this conference and also the opportunity to interact with the participants. Actually, my topic is sound and electromagnetic interference with the rare earth and polymer doped ferrite composite. So this presentation will a little bit cover about the introduction, and a modern material and small application and conclusions. So we know microwaves. The microwaves are the part of electromagnetic waves that ranges from 1 millimeter to 1 meter. The microwaves are not in the micrometer range. It is in the 1 meter to 1 millimeter range. In the frequency, it is called 300 megahertz to 300 gigahertz. So further, the microwaves are classified into three different categories like ultra high frequency, super high frequency, and extremely high frequency. The frequencies are given in the slides. So I already mentioned that the microwaves are smaller waves. It is the millimeter waves. It is not a micrometer wave, it is a millimeter wave. So further, as per the classification of IEEE band, the microwaves are classified into different bands like L band, S band, C band, KU band, K band, KA band. Like classifications are given. For example, the satellite communications, we are using the different bands. For the domestic applications, we are using the different kind of frequencies. So, in general, microwaves are not a harmful waves. Microwaves do not have the sufficient energy to chemically change the substance. But the continuous exposure of the microwaves are highly harmful. The microwaves are not harmful, but the continuous exposure of the microwaves are harmful. So during the Second War also, the peoples are used the microwave to train the brains of the soldiers. So the problem in the engineering, one is the electromagnetic interference. The electromagnetic interference is nothing but unwanted signal interfere in our systems. That is not a harmful, but that is a problem. Another one is electromagnetic pulses. That is very harmful. That is a high energy pulses interact with the system in a short duration that creates some very much of heat that can burst the systems. So that is a very dangerous one, electromagnetic pulses. So we are find out some material like electromagnetic compatibility. So the problem in the nature. You know the story of the movie? What is the movie? What is the story? Effect of radiation. So that is the problem here. So the radiation is very people affecting by the radiation is increasing day by day. So that is the problem. Nowadays, all the birds are, but the problem is microwaves are not harmful, but the continuous exposure of the microwaves are very harmful. So that only we are suggesting some of the material. This is how the people are affected by cell phone towers by the continuous exposure. So this is the absorption way. The microwave absorption is defined by conductivity loss, dielectric loss, and magnetic loss. It is sum of three: conductivity loss, dielectric loss, and magnetic loss. So this is the formula for the conductivity loss and dielectric loss and the magnetic loss. So the absorption power is directly proportional to the dielectric constant. Absorption power is directly proportional to the dielectric constant, but it is inversely proportional to conductivity. P is in directly proportional to sigma, but the sigma is depends on the magnetic parameters in inverse way. So this is the formula for the classical energy. Here, efficiency is directly proportional to sigma E. This is sigma E. Sigma E depends on the conductivity. So if you increase the conductivity, sigma AC will increase. So absorption power will increase, shielding efficiency will increase. Whereas if you decrease the MS, saturation magnetization of the material, mu dash will decreases. Here if you decrease the mu dash, efficiency will increase. So there are the two ways. One is increasing the dielectric constant, another one is to decreasing the magnetic property, saturation magnetization. So this is the electromagnetic wave, the symbolical representation of the electromagnetic wave. It is also two component. One is electrical part, another one is magnetical part. So the both are perpendicular to each other. The another one thing is electric and magnetic are perpendicular to the field direction. However, both are same in the amplitude at the same time. So electric and magnetic field are the same magnitude at the same time. So that's the problem with the electromagnetic waves. So that is the property of the electromagnetic waves. So the people are trying with so much of different element like FeCO powders. Here, the electric component is lower, but magnetic field is higher. In the similar way, cobalt powder also we find out. The solid copper sheets are efficient for electromagnetic shielding, but the power is very low there. Both are in the same order, but the power is very less. So some of the materials like Fe powder, alumina powders, and ZnO, but sometimes the magnetic is higher, electrical is lower. Here in a different way. So we are different with the WC powder, FeCO3, FeO powder. So here this is the ferrite material. This is the compound is Fe3O4 is one of the ferrite material. Here it is little bit comparable. So the electrical and magnetic losses are little bit comparable. So the people are working on the ferrite material. So this is the zinc and oxide cobalt also will give the good results. So the people are concentrating this kind of ferrite materials. So this is the formula for the phenyl ferrite. MFe2O4 is the general formula for the phenyl ferrite. M is a divalent element. Fe2O3 is a ferrite composite. So here, this is the lattice crystal structure of the phenyl ferrite. The property of the phenyl ferrite is determined by the two interactions. One is A site will be surrounded by some tetrahedral atom. B site will be surrounded by some octahedral atom. So the interaction between the tetrahedral and octahedral to determine the magnetic property of the materials. Another one is effect of rare earth. So in order to increase dielectric properties, people are doped with the ferrite materials or polymers, something like that. Another question, why the nanomaterials are focused? That's another question. This is the bulk material, this is the nanomaterial. One can easily see what are the changes that happen when bulk to nano. The energy levels are discrete. Here the energy levels are continuous. Here the energy levels are discrete. So the energy level, the space between the energy levels are very huge. Another one is band gap is tunable. So once we play with the nanomaterial, we can increase the band gap. Another one is magnetic property. We know the magnetic materials as a domain. So it has some multiple domains. Whenever we are applying the magnetic field, all the field will align in a uniform direction. After cut down the magnetic field, it will go to the random direction. So that is happened in a ferrite material. But when the people break the material into nano shape, so if you break down the material, all the spin will align in a uniform direction without magnetic field. So that is called a super paramagnetic field. So increase the magnetic saturation without any applied field. So another one is surface to volume ratio will increase absolutely for the nanomaterials. Nowadays the people are trying with the shape mineralize in the same one. We know shape mineralize. So they can regain its original shape. Actually, the nickel is some magnetic properties, so that will be used for capturing the sound. So the first I have did this one. We have prepared three different materials. One is copper ferrite. In this copper ferrite, I have doped 50% of Mn ferrite. In this same ferrite, we have introduced some rare earth. So in this case, we have increased the dielectric constant from 1.66 to 5.33 by doping of 50% is replaced by Mn and a small amount of La. This is the magnetic properties. When the copper ferrite has some like this, but the lanthanum dope will decrease the magnetic properties in somewhere around 30. So this is the series we have prepared. Mn Cu 50-50. So small amount of lanthanum will be doped in the Fe site. The doping ratio is S is equal to 0.25 to 1. In this, we have increased some dielectric constant from 4.62 to 4.84. Here, the same is. So the magnetic properties also we have studied. The magnetic properties also decreased from 70 to 40. Absorption properties. So here I have showed the band of absorption around the X band. Usually above X2, above 8 is called as the X band. So that at the 8 to 12 is X band. At the end of the X band, I have observed this kind of electromagnetic absorptions. So this is the comparison table. So by a small amount of doping, the band gap is increased. The dielectric constant is increased from 50 to 100. At the same time, the magnetization is decreased from 60 to 41. In similar way, we have prepared some other effect of radiation. That is another interesting study. I have prepared a material for electromagnetic absorption. That material is exposed some high energy radiation. So using that radiation, I have created some oxygen defect. Using this oxygen defect, that electromagnetic magnetization is decreased. So that will be used for shielding the electromagnetic waves. So this is our study. We have prepared the material. It has a magnetic station 55.49. That will be decreased to 3666. This is the effect of polymer. In this polymer, I have prepared the two series, nickel, lanthanum and neodymium. I put in the same composition. So the structural, there is no change in the structural properties. The dielectrical properties, here it is around 1400, here it is 1800. So the magnetical properties also in similarity decrease. It is around 100 here, it is around 80 here. So this is the comparison of the dielectric constant. This is without polymer. This is the with polymer table. So only how much dielectric constant has been increased by doping the polymer with the same composition. So this is the decrease in the magnetic saturation. Area of the magnetic saturation is 94. By adding the small PVA, that is decreased to 84. Here I am put the lanthanum. So the dielectric constant is earlier 329. By using a small amount of polymer, we have increased that is the 895. So this is another one, lanthanum doped calcium chloride, that is recently published in the Journal of Rare Earth. So here also we can decrease the magnetic properties and increase the dielectric constant. Here we have observed some effective electromagnetic shielding less than X band. Around the X band we have some electromagnetic absorption. So this is 3, SiO2, ferrite plus MnO2. There are so many combinations the people are trying now for bring out the material for electromagnetic shielding. So these are some of the combinations. You can try your own combination by 3 to 4 elements you can try. So now the people are 3, 1 to 3, 3 elements. If you wish, you can try with the different elements or different combinations. So nowadays, self-cleaning paints are available. So we can do. So this is the how the people observe can see the. So this is a hot plate. One side of the hot plate will be coated with the material. One side is empty. So here the temperature is 168. Here it is 198, 192. So you can see the difference between the two. If you put ice cube here, it will melt quickly. Here it can stand for some time. So this is the So it melts here easily, it won't melt here. So these are some of the applications of this thermal coating interiors.
Sir, for your information discussion and enjoy some. Also request everyone to arrive after 10 minutes.
பார்ட்டி ஸ்நாக்ஸ் அவைலபிள் இருக்குது. ப்ரெசென்ட் பண்ண 3 லொகேஷன் வென்யூ சொல்லியிருப்பாங்க. இந்த லொகேஷன் ரெஃபரன்ஸ் பண்ணி கொடுத்து வென்யூ 1 இதுதான். வென்யூ 1 வந்து இதான். வென்யூ 2, 3 பார்த்தீங்க அப்படின்னா ஒன்று வந்து 4th ஃப்ளோரில் இருக்கும், இன்னொன்று 3rd ஃப்ளோர். அதானே ஒன்று வென்யூ 1 இந்த பிளேஸ் தான். ஓகே, பேரலா பாத்தீங்கன்னா போஸ்டர் பிரசன்டேஷனுக்கு வந்து சாண்டி வச்சிருக்கோம். அந்த ஸ்டாண்ட்ல கொஞ்சம் பேஸ்ட் பண்ணிடுங்க. உங்க பிபிடியா முடிஞ்சாலும் உங்க பென்ட்ரைவ்லயே வந்து ப்ரெசென்ட் பண்ணிட்டு போயிடுங்க. நீங்க எதுவும் காப்பி பண்ண வேணாம்.
சீக்கிரம் முடிக்கணும். இவங்க 5 பேர் தான் முதல்ல கால் பண்ணுங்க. இது வந்து டிஸ்பிளே இந்த லேப்டாப்ல இங்க இருந்து பண்ண முடியுமா? எண்டு ஸ்ட்ரீம் கொடுத்துட்டுமா? அப்புறம் ஆன் பண்ணி ஓகே.